All right, peace, love, science. Science! Huh. Funky, funky science. Whoa. Funky, funky, funky science, yeah. Whoa. Funky, funky, funky science, yeah. All right, peace, love, science. Welcome to Funky Science Story Hour. I think this may be working. I sure hope it is. Can somebody give me a comment? Let me know if you're hearing me, seeing me, feeling me. Are you with me, people? I see a couple people have joined. Do we have sound? Somebody tell me. Oh, all good. Yes. Woohoo! All right. Welcome. I'm pretty psyched. This is a whole new thing I'm trying. All you funky science kids and immature adults. I'm here to basically try to answer your questions and tell you some stories. I'm gonna mostly take requests. I've been getting some requests in already on the Facebook page. All right, so what I want to do is start off, of course, with the Funky Science Story Hour theme song. I've just been putting this song together, and the theme song will evolve as science does through peer review. So this is the first version, the draft, the preprint of the Funky Science theme song. And then as we go along, we'll improve it. People will review it, they'll come up with alternate ideas, and just as science does, our ideas will hopefully get better. But anyways, here's version 1. Oh, sorry. Gather around my children, pull up a chair my friends. Let's all get together for the story that never ends. How did we get here? What's inside your head? What's bluer than blue? What's redder than red? Gather around my people, all children young and old. Pull up a seat, put up your feet for the greatest story ever told. Funky Science Story Hour, 'cause science is knowledge and knowledge is power. Because the world is weird, and weirdness is fun. 'Cause there's so much to learn, and we've all just begun. We can learn together, we can understand the weather. We can imagine ourselves in any place. We can see the earth from outer space. Yeah, with science. Funky, funky science. Science, science. Funky, funky science. Funky, funky, funky science, yeah. Yeah, science. Funky, funky science. Science, science. Funky, funky science. Oh, funky, 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 funky science, yeah. All right, welcome to Funky Science Story Hour. And I want to mostly just dive in and start answering questions that some of you cool kids have been sending. And The easiest thing for me is to read them off of the page, the Funky Science Story Hour page on Facebook, which is easier than reading them as they scroll by. Although I will try to do some of the scrollies too. But for now, I'm going to take some of the questions that you guys have been sending in, which are really great questions. For instance, oh, well, this is a softball one, but it's also a really cool one that somebody asked. This is actually one of my favorite questions. It's, why is the sky blue? And what I love about this question, and this is true about a lot of science questions, is that you can tell a story to answer it, and that story connects with a lot of other stories. And then it turns out all the science stories connect together, and they're all part of the one big story of how we figure out this amazing universe that we're living in. So why is the sky blue? That has to do with a couple of things. One is what we know about light, about what light is and how light works. And the other is what we know about our planet Earth and its atmosphere and how light travels through it. So the first part, if you want to know why the sky is blue, is to think about light. And also there's another cool way to set this up, which I'll do first, which is, what do you think the sky would look like if Earth had no air? We actually know the answer to that because we've had humans standing on the moon and looking up at the sky on the moon, and we've had spacecraft on a lot of other planets and moons that don't have air. And the answer is, if you were standing on the moon on a planet with no air, and you looked up in the middle of the daytime, of course, the sun would be right there, and it would be blazing bright, blazing hot, brighter than it ever is on Earth because it's being blocked by our atmosphere here. But you could just block out that sun with your hand. You say, "Sun, speak to the hand," and block it entirely. And if you did that so your eyes weren't blinded by it, the rest of the sky, even in the middle of the day, would be black as night, blacker than night on Earth, because there's nothing in between you and the blackness of space and the brightness of the stars. So imagine yourself on a planet without air, daytime, but you're blocking out the sun. The sky is black. It's dark. You just see the stars. Now here we are on Earth. We just jumped from the moon back down to Earth through the air, and we landed on our feet. And we're looking up in the daytime, and we don't see those stars. And you can ask, why is that? If I'm not looking right at the sun, the light's coming from the sun, why don't I just see the stars? One way to look at why is the sky blue is to say, in the daytime, why isn't the sky black like it is at night? And it has to do with light and the way light travels through the air on Earth. One way to think about light, okay, light's weird, and a lot of things in science are weird. The more we know and the more we try to describe the way they are, the stranger it gets. There's some weird things about reality that we've discovered through science, through experiments and math and theory. And one thing is that light, in a way, acts like little particles of something moving from place to place. So you turn on a light bulb, and there's little particles bouncing around the room and bouncing into your eyes, and that's why you see. They're tickling your optic nerves and sending a signal to your brain saying, "Oh, there's light in this room, I can see things." But another way to describe light is that light is little waves moving through space. And of course, light is made up of different colors. You know that, right? Blue, yellow, red. And what's different about those different colors? Why is it that some things look blue, some things look red, some things look yellow? It has to do with those waves of light moving through space, moving through the air. And we've discovered that it has to do with the wavelength. That is, you can picture the light as these squiggly little things moving through space. And the blue ones are shorter, smaller squiggles. We say they have smaller wavelengths. A blue ray is these little squiggles moving through space. Whereas if you go towards the red side of the rainbow, the red side of what we call the spectrum, then you're at longer wavelengths of light. So a red wave of light is more like through space or through the air. Now, of course, they're not really going that fast. They're going at the speed of light, faster than even I can move my hands. The speed of light is really, really fast. But the point here is that the blue light is little wavelengths, and the red light is longer wavelengths. And all the colors in between are different wavelengths. Now, that's one thing you need to know for our question of why is the sky blue. The other thing you need to think about is, again, go back to that story of daytime on the moon. The sky is just black. It's space. You're seeing space. On Earth, why are you not seeing space? It's because that light from the sun is coming down through our atmosphere, through all the air. Miles and miles of air to get to you standing there on the surface of the Earth. And that light gets bounced around by the particles in the air. The air is made of what we call molecules. They're almost the tiniest things there are, although molecules, as many of you know, are made up of atoms, and atoms are made up of smaller things, and it's like a little Chinese puzzle with things inside of things. But the basic bits of air that you're breathing and that we're moving through are made of things called molecules. And the molecules of air are tiny. And the light coming through sometimes bounces off some of those molecules of air, so that it's not coming just directly from the sun to your eyes. It's getting, before it reaches you, some of it is getting bounced in different directions off of air, and bounced off of more air, and bounced off of more air. So then when you look in any direction other than the sun, you're seeing light that has been bounced from molecule to molecule to molecule to molecule, and then is bouncing and finally bouncing into your eye. That's why on the moon, again, with no air, the sky is black, because there are no molecules of air. So all the light comes just from the sun directly to you. You're standing on a planet with air, so all that light has to come through the air, and a lot of it gets bounced around by molecules. Okay, so that explains why you're seeing light from the sun, even though you're looking in other directions, why we have a sky that's bright at night and you're not seeing the stars. But that doesn't explain why it's blue. That just tells you, if what I just said so far, you would think that the sky would be the same color as the sun. It would just maybe not be as bright, but it would be all the different colors of light mixed together. When you're seeing the sun, you're seeing all the colors of light mixed together. It looks sort of yellow-white because that's the mixture of red and yellow and blue and green, all those and orange, all those colors mixed together give you that color of the sun. But here's the magical thing, the cool thing that makes the sky blue. As that light from the sun hits those molecules of the air, they don't all react the same way. The blue light, with those little squiggles, hits the air molecules a lot and bounces around a lot. The blue light has trouble making it through from the sun to your eye, because those little waves of light, they're much more, it's harder for them to get around the air molecules because they're little. They hit the air molecules and they go, whoa, and they bounce in a different direction. And then they're going that direction and they hit another air molecule and they're like, whoa, and they bounce in a different direction. We call that scattering. Scattering of light is when it's hitting things and bouncing around in different directions. So as a result, the blue light is getting bounced everywhere. Now the red light and the other light that's almost red, the orange, and the non-blue light, the longer wavelengths of light that are more like, they don't hit the air molecules as much, or if they do, they're not bothered. They're big, and they don't get scattered. They just keep going. The little blue light rays get scattered all over the sky, and you see them coming from all directions. The yellow and the orange and the red light rays that are longer wavelengths they don't get scattered by the air molecules as much. So you don't see them. You only see the blue when you look in other directions. They're the ones getting scattered. You know, it's a little bit like, I just thought of this. Imagine you have a whole bunch of dogs. I love dogs. Do you like dogs? Imagine you have a whole bunch of dogs. And some of them are tiny little dogs like Chihuahuas. Or, what's another small dog? Dachshunds, yeah. Imagine you have some dogs that are like these little dogs. And then you have all sizes of dogs. And then you have some huge dogs like some Great Danes and some Mastiffs. They're practically horses, but they're dogs. Now you put all of them at one end of a field, and then imagine in the field there's some little bushes, say this high, okay? And you set them loose on that field. Now the big dogs, the Great Danes and the Mastiffs, they're going to go running through the field. Ka-toom, 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 ka-toom. They're not even going to care about those bushes. They're just going to step over them. You know, we're big dogs. We don't care. They're like the red light. Whereas the little dogs, the Yorkies, the Dachshunds, the Chihuahuas, they start going and they're like, I can't get around these giant bushes. And they like scatter in every direction, and they get lost, and it takes them. They can't just go straight through the field. They have to avoid the obstacles. So, in this analogy, we're making an analogy here. An analogy is when you say, this thing happening is sort of like this other thing, and it helps you understand something because you understand the other thing. So we're making an analogy here. We're making an analogy between big dogs and little dogs, and big, long wavelength light rays, like red light, and little tiny short wavelengths like blue light. So again, that light coming from the sun is like the mixture of the dogs, and the little ones can't just make it straight through. They get bounced all around. That's the blue stuff. So when you look up at the sky, you're seeing those short wavelength blue molecules that have been scattered all around. And when you look just at the sun, you're seeing the rest of the light that has not been scattered. The shorter wavelengths, the blue light gets scattered more. So when you're looking away from the sun, you're only seeing the scattered light, not the direct sunlight. That is why the sky is blue. Yay! I hope that makes sort of sense. By the way, another related question you might ask. Okay, so that's why the sky is blue, but why are sunsets red? Good question. Well, it's related to the same. Wait, what if I don't like dogs? Well, Keith asks, what if I don't like dogs? Will that color my reality? Yes, Keith, that's a really good question. I'm glad you asked. If you don't like dogs, you should go on to a different Facebook Live, which is being run by a psychiatrist or a support group for people that are emotionally, I don't know, the people that don't like dogs. I can't help you. That's not in my pay grade. But thank you for that, Keith. but so now we know why the sky is blue. But why are sunsets red? If I may, I'm going to try something. I don't know if this will work. I'm going to use this really cool piece of technology that your parents used to use when they were in school. This is called a blackboard. And this is chalk. Let's see if this works. See if you can see. Oh, you can see. This works. I love technology. All right. So this is the surface of the Earth. And this is you. Right? That looks like you, pretty much. To first order. Scientists say to first order. That means if you don't look at the details and you just look at a crude simulation. To first order, this is the Earth and this is you. And now, here's the atmosphere. This is not to scale, as we say. It's really much bigger. If this were you, the atmosphere would be much higher. But the point is, if that's the atmosphere, and if the sun is overhead, here's the sun, and the light is coming straight to you, and then you're seeing that yellow light, but of course that other light, as we mentioned, some of it's being scattered in different directions, and I should use a blue pen for that, for the light that's being scattered. And then you're seeing, when you look up, you're seeing that blue sky of all the scattered light. But then, imagine how the picture changes when it's sunset. Let's say the sun's over here now, because, of course, the Earth is turned. That's another story, but you probably know that. We can get into that. But the Earth is turned so that, or actually, let's do it. In fact, let's not move this. Let's move you, because that's more realistic, right? So the Earth is turned, it's 6 hours later, right? In 6 hours, you've rotated a quarter of the way around the Earth. In 12 hours, it's midnight, you're down here. In 18 hours, it's going to be sunrise again. In 24 hours, you're going to be back in the same place. So let's say it's like 5 hours later or 6 hours later, so that 5.5, so that the sun has almost set. So now you're standing here, and the sun is still there. Now look, the point is, here's the sun's rays reaching you at sunset. And look how much more air the sun has to go through. It has to go through a lot more air to reach you, because this geometry of the atmosphere is such that the shortest path of light is if the sun's right overhead. That's the shortest amount of air. If it's coming at an angle like this, the light is traveling through much more of the atmosphere, much more of the air before it reaches you, right? And if that's the case, then much more light is going to get scattered out. And by the time the light reaches you at sunset, all of the blue light has been scattered out. And what's left, or almost all of it, what's left is mostly the red light that's reaching you. So the scattering is a lot more at sunset, because the light has to go through much more air to reach you, right? That makes sense, right? Now, another interesting thing is that it's not just air molecules. Like air molecules are like oxygen is like two little oxygens, like that, two little atoms bouncing around. This is a giant drawing of an air molecule. It's not just the molecules of the air that are bouncing and scattering that light. It's also when there's dust or smog in the air, it scatters light. And this is why it's not just sunset that can turn the sun and the sky around it red, but it's also when there's smog, when there's a dust storm, when there's a forest fire, so there's a lot of smoke and ash in the air, when there's a volcano, which puts a lot of ash in the air. Any of that, it's not just molecules. Then there's a lot of particles in the air of smog or ash or dust. And those particles can also scatter light. And again, they preferentially scatter the smaller wavelengths of light, although not as much, but that's technical. But anyways, that also leads to more scattered light, and is why when it's smoggy or when there's dust, the sky also has that beautiful red color. So anyways, when you ask a simple question, like why is the sky blue, you end up telling, if you really want to try to answer it, you end up telling all these stories about what is light, and how do our eyes see light? Why do we see anything at all? And what's the Earth's atmosphere like, and what is happening when the sun's rays come through the Earth? That's why I love science, because every story leads to other stories. Okay, I'm gonna take another question from the page here. Zane wants to know, how big is the moon? Hey Morgan, hey Zane. Okay, Zane wants to know, how big is the moon? It's pretty big. Okay, next question. No, I'm just kidding. The moon, it depends on what you compare it to, but it's the thing we usually point out is that the moon is much smaller than the Earth. How much smaller? It's about 1/4 the size of the Earth. So if the Earth is this big, and the Earth is about 8,000 miles across, right? You know how big a mile is, right? And the Earth is about 8,000 miles across. Well, the moon is about 1/4 that size. So it's about 2,000 miles across. So the moon is a pretty big object in space. It's big enough so that it's round. The big planets and moons and asteroids are all round because when they're large enough, gravity pulls them into a round sphere. So anything above a certain size in space, planets, moons, whatever, are round. The moon is much bigger than it's plenty big to be a round object, but it's much smaller than the Earth. Well, it's about 1/4 the size of the Earth, which means that you could fit about 8 moons inside the volume of the Earth. Like if you were somehow able to melt the moon and pour it into a container the size of the Earth, you could do it once, you could do it twice, you could do it 8 times, and after you did that 8 times, it would fill up the Earth-sized container with melted moon stuff. Although here's something interesting. You might think because the Earth is 4 times the diameter of the moon, and therefore 8 times the volume, 8 times the size, 3D size of the moon, you might then think that Earth weighs 8 times as much as the moon. However, that's not true. The Earth weighs significantly more than 8 times as much as the moon. And that's because the Earth and the moon are made out of different stuff. They're made out of a lot of the same stuff. Moon rocks, it turns out, are similar to a lot of kinds of Earth rocks. But Earth, in the center of the Earth, has this huge metal core, this huge iron core in the center. And iron is really heavy. Iron is twice as heavy as rock. And the moon doesn't have that. The moon doesn't have that heavy iron core. And so the moon is actually what we call less dense. That is, a certain bit of it. Let's put it this way. If you took a moon-sized chunk of the Earth, it would weigh a lot more than the moon because Earth is more dense than the moon. So that's the basic answer, Zane. Of course, you can ask follow-ups. And yeah, that's true. I saw a good comment from Yila. Melted Moon Stuff is a good name for a band. It's funny you say that, Yila, because you know, I've been in a lot of bands in my life. It's another thing I do. You can see I have some music stuff. And the very first band I was ever in, my junior high school band, was called Liquid Earth. That's true. I was in a band called Liquid Earth. And when I was in like, you know, 7th, 8th grade, that was my first band. And then I was in a band called Hyperdrive. And then I was in a band called The Geeks. I could tell you all the bands I've been in, but that would take way too long. And we're doing some science here. Oh man, Lauren from Maine wants to know what you think is beyond the known universe. Great question, Lauren from Maine. That's a hard one, but I like it. I like the hard questions because you even have to think, you know, how do we even approach that question? And I like the way you phrased it. Lauren wants to know what I think is beyond the known universe. So she's not asking, Lauren is not asking what is beyond the known universe, which is a slightly different question. The question is, what do you think is beyond the known universe? And this is a time, before I try to answer that, for me to say something about science, which is that science really is not about having all the answers. Science is about an approach, a way that we investigate the universe. We have ideas, we try out the ideas, we make predictions and see if those ideas work. And then sometimes people come along with better ideas. And then we say, oh, you're right, that's a better idea. And so science changes. And there's some questions which science does not have the answer to, but we still have some what we call speculations. Speculations are when we use what we know to try to say something about the... Oh, thanks, Graham. Graham says volume scales with the cube of the radius, so the moon's volume is roughly 2% of the volume of the Earth. Oh, I was totally... Well, I was thinking a factor of 4 in radius. So a factor of 4 cubed. I was totally wrong. See, as I was saying, science gets corrected all the time. So it'd be 4 cubed. 4 times 4 is 16, times 4 is 64. So take back everything I said. The moon is 64 times the volume of the Earth. If you were pouring moon into Earth, you couldn't. If you poured 8 moons into the Earth, you would just have filled a little bit of it. You have to pour 64 liquid moons into the Earth to get a whole Earth's worth of volume. Thank you very much for that, Graham. See, real-time correction. I love it. So Lauren asked, what do I think is beyond the known universe? And that's a great question. What do we even mean by that question? What do we mean by the known universe? In a certain sense, there can't be anything beyond the universe, because the universe, the term means all that is. Uni. One. Uni is one, like a unicycle has one wheel, right? So the universe is all that is. And yet, if we define the universe, and this is funny, there are different ways we can think about the universe, and in some of those ways, we can say what's beyond the universe. And for instance, you might know about this, but of course, we talked about light earlier. And the way we see things, the way we perceive and measure things, is through light. You're seeing light coming off the screen now, and you're seeing me, but that, of course, is because the light is traveling through this room and bouncing off my big shiny nose and into the camera of my iPad here, and then out of the screen and into your eye. So, Uni is one. Sounds like a punk band name. You know, if we get anything out of this session, we're going to have a whole bunch of good band names by the end of this. Okay, so the universe, in a certain sense, is all that is, except for because we see things and we perceive things through light, that means it takes time to see things, which is a weird concept because we're all so close together. And even, the moon, we talked about the moon earlier, the moon is far enough away so that it does take a couple of seconds for a signal to bounce off it. That's why when you hear the astronauts' voices on those tapes of the Apollo astronauts, and they go, Apollo, you're looking good. And then you wait, and they go, Houston, thanks, we feel good, Houston. But there's like a 2-second delay. That's because the radio signal is moving at the speed of light at that distance. It takes a while. Now, when we talk about the universe, we're talking about things that are so far away that even the speed of light, which is the fastest thing we know, it's the fastest thing we think, according to our understanding, nothing can move faster than the speed of light. So it defines the fastest speed in the universe. And when you're talking about distant galaxies and clusters of galaxies and the biggest structures and the farthest structures in the universe, they're so far away that even at the speed of light, the fastest possible speed, it can take millions of years, hundreds of millions of years, for the farthest things away, billions of years for that light to reach us. They're so far away, and there's a limit to how far we can see with light, because as we understand it, the universe is only about 13 billion years old, and it's been expanding that whole time. There are things so far away that we can't see them. We can't, even with the best telescopes, even with the most imaginable telescope you could build, the best imaginable telescope, there are things farther away than can be seen at the speed of light, which is the fastest speed there is. So that's why we talk about the known universe or the visible universe. And we don't know what's beyond it because we have no direct way of finding out. We have theories and there are different ideas about it, but there's places that are so far away that we can't see them even with the best telescope you could imagine building. So that's what when we talk about being beyond the visible universe. And then we have some There are scientists called cosmologists. Cosmologists are people that study the origin and overall size and fate of the universe. Not to be confused with cosmologists, or people that, help you with your complexion. That's a cosmetologist. I'm talking about cosmologists. A lot of cosmologists have bad skin because they're no, I'm just kidding. Cosmology and cosmetology have nothing to do with one another other than having similar names. But cosmologists have ideas about what might be beyond the visible part of the universe, but they don't all agree, and we don't know. In science, you definitely have to be able to get to the point where you say, we don't know. And in this question, I'm going to say that ultimately we don't know. There's even this weird idea, you may have heard of this, that there are other universes existing in different dimensions in parallel to our universe. So there might be something called the multiverse, which is our universe, everything we know, everything we could possibly observe. And then there are other universes that started out separately and have evolved differently. And that's the idea of the multiverse. To me, that idea is a little bit beyond science. Some scientists like to talk about that stuff. To me, it's like talking about, well, maybe there's a purple unicorn in some galaxy that we could never observe. It's an interesting idea, but is it a scientific idea? How are you going to observe it? So it's more like an interesting story to tell, but it may not be science. But there are some scientists who have some ideas about how you might test the multiverse. But anyways, that's getting pretty far afield. Let's see. I want to take one more question, maybe play another song, and then we'll see how we're doing. Dylan, age 6, says, how does it feel on Mars and in the red spot? How does it feel on Mars? How does it feel on Mars? How does it feel on Mars? Well, the first thing I would say about how it feels on Mars is that the gravity is different. So no matter where you are on Mars, if you're inside a habitat, underground in a cave, in a spacesuit, all those things might affect the way it feels, but no matter where you are on Mars, gravity is going to be much lower. So it's going to feel really different just to stand there and to walk. You've seen those videos of the astronauts on the moon, and then they try to walk. They're sort of, instead of just walk, they're like, and they can jump high and everything. Well, the moon has about 1/6 the gravity of Earth. Now, Mars has a little bit more gravity than that. Mars has about 1/3 the gravity of the Earth. So, what is gravity? Gravity is this force where everything is pulling on everything else in the universe all the time, and the more mass there is, the heavier, the bigger something is, the more it pulls on everything else. So it's because the Earth, as we talked about before, is much bigger than the moon, that's why the gravity here is much stronger, the pull of gravity that makes how it feels to stand on the Earth and makes you weigh a certain amount. Now on Mars is a lot bigger than the moon, but it's still a lot smaller than the Earth. The diameter of Mars is about half of the diameter of Earth. And Mars is also less dense than Earth. It does have a core, probably made out of metal, but not as big a core and not as dense. So Mars is smaller than Earth and would weigh less for the same amount of Mars stuff compared to Earth. All that adds up to Mars having about 1/3, Mars having about 1/3 the gravity of Earth. So if you're walking around on Mars, it wouldn't be quite like those videos of the moon, but it would be a little bit more like, it would be, you'd have more of a spring in your step, you could jump farther. I think you would eventually find a new way of walking. I got a new way of walking. You'd find a new way of walking that would take advantage of that. And I think people who spent time on Mars, they get good at it. And you could probably go really fast and jump really high. And could you imagine doing dance? Can you imagine dancing on Mars? How cool would that be? Think how high you could jump. Think of the moves you could make. God, think of just the acrobatics you could do. Think of the extreme sports, base jumping off of cliffs. Ooh, you'd fall slower. You still have to be careful. You'd still hit rock. And I don't want to encourage any irresponsible behavior on Mars, kids, but still, I think it would be pretty cool. So, so the first thing is how it would feel would be the gravity would be lower, no matter where you were on Mars. Everything else would kind of depend on the habitat you were in. I mean, you could not just go out on the surface of Mars without protection. It wouldn't feel like anything. You'd be dead. Sorry to say, because there's very little air there. We talked about the air on Earth and how the sky would look and everything. Mars has much less air. On Mars, the surface pressure is about roughly 1% of the surface pressure on Earth, or 1/100th. So you have to go up really high in Earth's atmosphere, way up in an airplane, to get to altitude where the air is as thin as it is on the surface of Mars. And there's no oxygen in that air. It's almost all carbon dioxide. So you couldn't breathe on Mars, and you also you have to be very careful because of the radiation. Just like on Earth, you can get sunburnt if you're not careful. On Mars, you can get fried if you're not careful because there's really intense radiation coming from the sun that on Earth is blocked out by the thick atmosphere. On Mars, it's going to reach the surface. So the first thing is you could not feel what it would be like to be on Mars just standing around in your clothes on the surface because you couldn't live. But so let's assume that then you're in some kind of a habitat. Or you're in a spacesuit, or you're in a Mars buggy that's got a protected bubble, so you're okay because you've got air to breathe and you've got some kind of shielding from the ultraviolet rays of the sun. Then you would still notice some other things other than the gravity. For one thing, because Mars is smaller, in some places at least, you would notice that the horizon didn't seem so far away. Now that's an effect that would be subtle a lot of places because it depends. Mars is still big enough so there's mountains and valleys and it would depend on the topography. But on average the horizon wouldn't seem as far away because the planet it's smaller, it curves more. And the light would look different because the atmosphere is thinner, but also on Mars the atmosphere is full of dust. And even though that atmosphere is so thin, there's tons of wind a lot of times. I mean, the wind varies, but it has these fierce windstorms and dust storms sometimes. And so it comes and goes, but sometimes the air is full of dust. Sometimes it's less dusty. And because of that, the sky on Mars is actually pink. And it changes in color. Sometimes it's more blue, sometimes it's never the deep blue of Earth because it don't have all that air that we talked about that makes the sky blue. But all that dust does scatter a lot of light, and depending on how dusty it is, because depending on how many dust storms there have been, it can be more or less pink, but it's also often pink. And also Mars doesn't have a big moon like the Earth, but Mars has two little moons called Phobos and Deimos. And those two little moons are, Phobos and Deimos, those words mean fear and death. And they're tiny little moons, but you would be able to see them move through the sky night after night on Mars, just like we see our moon move through the sky, which that would be pretty cool. So I don't know, that's kind of all I got at the moment for how would it feel to be on Mars. Anybody mind if I do another song? I'm gonna, this is, I said in my initial announcement of this thing that I would do Puff the Magic Dragon, and it is a favorite song of mine. Now, honestly, to be totally honest, I have not practiced this, and it's been several years, but I think it's probably just in my head, I hope. I might forget the words, but I'm gonna try it. Puff the magic dragon lived by the sea and frolicked in the autumn mist in a land called Honolulu. Puff the magic dragon lived Jackie Paper loved that rascal Puff, and brought him strings and sealing wax and other fancy stuff. Noble kings and princes would bow whene'er they came. Pirate ships would lower their flags when Puff roared out his name. Oh, I forgot. Together they would travel on a boat with billowed sail. Jackie kept a lookout perched on Puff's gigantic tail. Puff, the magic dragon, lived by the sea and frolicked in the autumn mist in a land called Honolulu. A dragon lives forever, but not so little boys. Painted wings and giant rings made way for other toys. One gray night it happened, Jackie Paper came no more, and Puff, that magic dragon, he ceased his fearless roar. Oh, Puff, the magic dragon, lived by the sea and frolicked in the autumn mist in a land called Honolulu. Puff, the magic dragon, lived by the sea and frolicked in the autumn mist in a land called Honolulu. His head was bent in sorrow, green scales fell like rain. Puff no longer went to play along the cherry lane. Without his lifelong friend, Puff could not be brave. So Puff, that mighty dragon, sadly slipped back to his cave. Oh, Puff, the magic dragon, lived by the sea and frolicked in the autumn mist in a land called Honolulu. Puff, the magic dragon, lived by the sea and frolicked in the autumn mist in a land called Honolulu. All right. Yay! You know, it's weird. I cannot hear your wild applause. But I can totally picture it and feel it. Thank you, thank you, thank you. I see the little hearts on the screen. To me, that is wild, like applause. Okay, well, shoot, we're almost through with our hour here, but I'm gonna do lightning round of a couple more questions. The thing is, with these questions, you can do long answers, and sometimes it's tempting to go off on a tangent because you say, "Oh, well, that reminds me of gravity, and gravity's cool, and that reminds me of light, and light's cool." But yeah, you can do. I'll try to do some quick answers. So Brett Schock says that Carson, who is 9, Carson from Seattle, wants to know if there's life on Mars, is there life on Saturn, and would an elephant survive in space? He's been a fan of you since we watched your Denver Planetarium concert videos when he was like 3. Oh man, Carson, I love you. I know I don't know you, but I just have a really good feeling about you. I think you sound like a really cool person to me. Anyways, I will attempt a quick answer. Is there life on Mars? We don't know. This is one of those science questions that, you know, this is pushing the edge. We have ideas about it that are based on science. In fact, this is what I do with my science and what Graham does with his science and a few of the other people here. We study these questions. We try to understand life on Earth and try to understand conditions on places like Mars, ask how did life get started here? Would it have gotten started there? What can we learn about Mars that will answer this? So far we don't have the answer, but we've learned, here's some things we have learned. That early on, when Mars was a young planet, it was much more like Earth is today. I'm talking more than 4 billion years ago. So Earth is 4.5 billion years old. So I'm talking between 4 and 4.5 billion years, maybe up to 3.5 billion years. So the early part of Mars's history, way back then, we know that it was much more like Earth. We see dried up riverbeds. We see lakes, craters with lakes in them. Our rovers have found rocks that we know were made in water. So we know the problem with Mars today, if you were going to be a life form maybe trying to live there, is that it's very dry. There's no water on the surface. There's probably some water underground, but not much. And that's a big problem because life, as we understand it, needs water. But so we see evidence that Mars early on was a watery planet. And we're still trying to understand that history. What happened to that water? And did life evolve on Mars when it was wet? And if so, where did the life go? Did it die out when Mars lost its surface water, when the oceans of Mars dried up? Did all the Martian creatures die? Or did they find a way to live? Maybe some of them went underground, because we think that maybe there's underground water on Mars. And we're still trying to understand that. We see some signs. I was talking about gases and molecules before. There's a kind of gas called methane. And methane is something that we found on Mars, just little tiny bits of it. But what's cool about methane is that on Earth, the methane in the air is made by life, made by little microorganisms, by little bacteria. So when we see this methane on Mars, we go, if life on Earth makes methane, and we see methane on Mars. So there's some hints there, but the thing about science is we have to be skeptical, meaning you are not sure about things, and you look for other explanations because you don't want to draw a wrong conclusion. So that methane on Mars could be from Mars bugs underground, which would be cool, but it could also be from some chemical reactions happening in rocks or other things. So we don't know if there's life on Mars. The surface of Mars today, I can tell you, is not a good place for most life forms from Earth because of all that radiation from space and because it's so cold and so dry. But underground on Mars, buried under a little bit of rock so that you're shielded from the radiation, and deep down enough so that there maybe is some water. Who knows? We're still looking for the possibility of life on Mars. Okay, Carson, you also asked, is there life on Saturn? Again, I would say, we don't know. But if I had to guess, and I do have to guess, I would say it's less likely than life on Mars, but not impossible. If there was life on Saturn, it would have to just be in the atmosphere, in the clouds. There's no surface on Saturn. You go down in the clouds, down and down, and you get to a point where it gets so hot and where the pressure's so high that things would just be crushed, and it's too hot for the kind of chemistry that allows life on Earth to live. So in the air of Saturn, could there be some kind of life that we don't know about? I'm not going to say it's impossible. It's not the first place in the solar system I would look. However, there are 2 moons of Saturn. You know, Saturn has all these moons, and some of them are icy, and well, they're mostly icy, but some of they're different in a lot of ways. But there are 2 moons of Saturn that are both very interesting to astrobiologists, people like me that want to try to find life elsewhere. There's one moon called Enceladus, which is a pretty small icy moon of Saturn, but we know it has liquid water inside, and it's even squirting liquid water out into space through these geysers. It's literally gushing water into space. So could there be something living in that water inside this ice moon of Saturn called Enceladus? Maybe there could be, and we want to send a spacecraft out there and scoop up some of that ice and water that's squirting out of Enceladus and see if there's any bugs in it. It's possible. So that's a place. But there's also another moon of Saturn called Titan. And Titan is one of my favorite places in the solar system. It's a big moon. It's one of the biggest moons in the solar system. It's really, it's big enough so that if it was just orbiting the sun, we would call it a planet. It's substantial, and it has a thick atmosphere. Most moons don't have atmospheres, like we were talking about before. You look up into the sky and you just see the stars, no air. But Titan is a moon of Saturn with a very thick atmosphere, so thick that if you were standing on the surface of Titan, you would not see the stars. You would just see this very dusky, reddish atmosphere. And Titan, like Earth, has an atmosphere that's mostly made out of nitrogen. And it also has a lot of, there's a kind of molecules, we were talking about molecules before, there's a kind of molecule called organic molecules, which are basically just molecules that have the atom carbon and other stuff. And some of them are pretty big and complicated. And by the way, that's what you are and I am. We are organic molecules. That's what's so interesting about organics and organic molecules, is that that's what makes life. On Earth, that's what makes life. And astrobiologists think that a good way to find life elsewhere is to look for organic molecules that are doing interesting things and combining in interesting ways and maybe even forming life. And one thing that's very cool about Titan, in addition to having a thick atmosphere and having, believe it or not, rivers and lakes and clouds and storms, but not with water, with methane. It's very cold there, so the rainfall and the lakes are methane, which on Earth is a gas. It's natural gas. It's what's coming out of your stove. It's what's in your farts. Is also methane. So that stuff, like it or not, is all over Titan, but there's also lots of organic matter on Titan. In the atmosphere, raining down from the sky, pooling on the surface, forming dunes, organic dunes that are blowing around. So that's why, as astrobiologists, we're very interested in Titan, and who knows, maybe there's even some kind of weird life there. So, sorry, that was kind of long, but Carson, so the answer is that there's probably not life on Saturn, although we know so little. We're still trying to understand life in the universe. I don't think you can rule it out. But there are 2 moons of Saturn where, yes, I think it's a good place to look, Enceladus and Titan. And your final question, would an elephant survive in space? It depends. Carson, it depends. Does this elephant have an elephant spacesuit? If an elephant had an elephant spacesuit, then of course it could survive in space. And elephants are pretty smart, and they're pretty social. The only downside of elephants in space is that they weigh a lot, and it's hard to launch heavy things into space. It costs more. But, I bet one of these days there'll be the first elephant in space. But all I would say is that before we send elephants into space, let's make sure we develop a really safe and good elephant spacesuit. And you have to think about the spacesuit having like a trunk compartment where not only is it flexible and there's the right oxygen, but also elephants grasp things with their trunk, right? So the spacesuit engineers are going to have to be very clever to think about how you would build the trunk part of the elephant spacesuit so the elephants could actually grab things in space, right? I think that's going to be my answer for now. And I see that we are out of our funky science story hour. We've gone an hour. I love doing this. I could do it all night, but I think maybe we should call it. And then if I'll look at the feedback I get from this. I want to know how well this worked. If I should change how I'm pitching things, how I'm discussing things. If you like what I'm doing, should I do this again? Should it be the same? Should I switch from Facebook Live to something like Zoom? I see the pluses and minuses. So I'm very interested in your feedback. And by the way, feedback is a really cool topic. I think the next Funky Science Story Hour some of it will be devoted to feedback, the concept of feedback. But you know what? Maybe I'll close by, if you're still with me, by trying to once more redo the Funky Science theme song. After all, I just wrote it today, and I'm still working on it. Whoa, don't smash the guitar, it's not worth it. As in all science and all funk, the Funky Science theme song is a work in progress, and I still have to kind of read it a little bit. Whoa, Jesus. Huh. Sorry, I did not mean to use the Lord's name in vain, but I did. All right. Bit out of tune. On another Funky Science Story Hour, we can talk about what does it mean to be in tune? Why do frequencies of musical notes change when you change the tension on a string, and why does sometimes sound good and sometimes bad to us? There's a science to that too, which is everything is science if you think of it just goes to show you can get shown the light in the strangest of places if you look at it right. All right. Gather round, my children, pull up a chair, my friends. Let's all get together for the story that never ends. How did we get here? What's inside your head? What's bluer than blue? What's redder than red? Gather around, my people, all children, young and old. Pull up a seat, put up your feet for the greatest story ever told. Funky Science Story Hour, 'cause science is knowledge and knowledge is power. Because the world is weird and weirdness is fun. There's so much to learn, and we've all just begun. We can learn together, we can understand the weather, we can imagine ourselves in any place and see the earth from outer space. With science, funky science. Science, 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 funky, funky science. Funky, 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 funky science. Yeah. With science. Funky, funky science. Yeah, science. Funky, funky science. Funky, funky science. Funky, 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 funky science. Funky, 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 funky science. Alright, that's it. Peace out. I love you all. Be safe. Be healthy. See you next time. Alright. Peace, love, science. Science! Huh. Funky, funky science. Oh, funky, funky, funky science. Yeah. Oh, funky, funky, funky science. Yeah. All right. Peace, love, science.